Okay, guys. Because there some people have pointed me to the confusion that may have arisen. So I'll just start with saying something about the exam, and then most importantly, point 4. It's an open book exam, or even better, it's open material. You can bring, or as far as I'm concerned, anything you like, even your laptop or iPad. But of course, you're not allowed to communicate. So if you do that, then I want you to put it on airplane mode. Yes.
Can we bring Google?
If you download Google beforehand, then I'm fine with it. Yeah. Yeah. So that's it. So, well, and while we're at it, okay. So you have 3 assignments for 25 points. This exam is also weighted 25 points. Of course, the exam you make alone, the assignments you could make in groups. And because this is the only individual, really truly individual test we have, this is must pass. So and that means by virtue of the UR that you have to have 5.5, 5.5 or higher. So that's the rules. Then it will be organized as follows. I will give you 3 questions. The first 2 are 10 points each, and we'll have a small calculation in them. And the last question is a proposition, a stelling, which I will give you, and I want you to accept it and reject it, and give an argument why you think that proposition is true or false. I put a complete test in this format on Canvas, also with the answers with it. That is what you can expect. Apart from that, on Canvas there are a few test questions. These are older exams or older questions, so so sometimes they may be a little bit different than what we did here, but I think you can practice with them. And there's also a document that lists more or less point by point what the topics are that we discussed and what I want you to know about them. On that same note, that's what I actually want to do today. I'm not going to tell you anything new here. I'm just going to run by all the topics and then briefly stress the points that I think are important. Yeah, there we are. Okay. So on gross, we can divide the course into yeah. So
is PowerPoint going to be on campus too?
Of course it is.
Oh.
Actually, I think it already is. So we have we discussed some fundamentals, and then after that, the guest lecturers went more into the application side of things. So basically, so if we go through them, then we have the absorption and scattering properties of particles and tissue. Where tissue is then modeled as collections of particles. We discussed the volume fraction dependence of absorption and scattering properties. So a few slides on that a little bit later on. Monte Carlo was a big topic. We had one class on the radiative transport and the fusion of observation. That was one of the workhorses that can take also I think in Maurice's here. Basically the slides for that are the materials and also the chapters 1, 2, and 3 of the book of Vagene give you a good overview of the field and some of the topics that are here. Chapter 5 of that book is solely about Monte Carlo simulations. So a lot of the things that we talked about are there in book format. Then for the application topics, I'll point to the slides as well, of course, and also to chapter 18, which is an OCT. Yeah. Okay, so about fundamentals. the most fundamental properties, let's say, that describe absorption are the absorption efficiency, cross-section, and coefficient. So I want you to know what these are, what the units are, how we interpret them. If I give you one and some additional information, then you can calculate the other. That is basically things that go around that. Of course, you illuminate the particle with intensity. So what are the units of intensity? These things. I want you to be able to do a calculation with that. So we have incident. We have intensity. We have powers. So it's the relation between the two. What are the units? So here briefly are the definitions again. These slides are on purpose. And the class slides, so I'm not going to go through them very big. What happens here for absorption? So we have the efficiency, the cross-section, and coefficient. We also have for scattering efficiencies, so cross-section, scattering coefficient. But also for some of the processes that you encountered later on. We had you can, for example, define a fluorescence efficiency. That is then the amount of power that is turned into fluorescent into the power of fluorescent light. You can also define a Raman efficiency, which is then the amount of incident power that is transferred into the power of Raman photons. Marloes, I think also talked about efficiency for the second harmonic process. Yeah.
You said Raman, Raman for the scattering process.
Yeah, potato, but yeah, Raman. So that means that anytime you can have efficiency, that also means that you can, if you know the diameter of the particle, you can calculate the cross-section for the process. And if you know the concentration of the particles, you can calculate the coefficients for these processes. So we talked about them a lot for absorption and scattering, but also for these other processes. The interpretations are always the same. That is the
the absorption coefficient, we have to calculate that when you use probe, you have kilograms per cubic meter. So where is the kilogram?
Yeah, because it's not. It's per cubic meter. Rho is the number density, so it's the number of particles per volume.
Okay.
So the units of rho are per cubic meter.
Okay. Yeah.
But that benefits. Then we talked about this wondrous effect that if you have a fixed number of absorbing molecules and you place these molecules in suspension of particles, so they're encapsulated in particles, or you have them free floating in a solution, and you will do a Lambert-Beer measurement. So you put it in the cuvette, then you will measure. Your measurement will yield different absorption coefficients, just caused by the fact that in one situation the particles are placed randomly, and in the other situation the molecules are encapsulated in for example, red blood cells. That was called absorption flattening. The materials in the slides, but there is also an extra document that shows you the calculations. These were the equations that came out of it, and I want to so let me briefly stress that in such an equation there are three absorption coefficients. So the absorption coefficient of the molecules in suspension, so the molecules are encapsulated in the particles, and there you do measurement, or the absorption coefficient of the solution, and the molecules are in a solution, and then the UA, the molecular UA, that is the absorption coefficient that you would measure if one of the particles were actually a cuvette. So if you would measure through one particle only, then this is what you measure. So these two the most important biological application of this effect is in blood, where the hemoglobin molecules are absorbed, so they are encapsulated in red blood cells. So here, for blood, you would have an absorption coefficient measured on the blood samples. It would be like drawn blood. This would be the absorption coefficient if you would break all the cells in that blood sample and then do the measurement. And this would be the absorption coefficient that you would measure if you would isolate one single red blood cell and calculate the absorption. That's the interpretation of these numbers. So I want you to be able to put these things together. Of course, we along the way a couple of chromophores were discussed. Chromophores are light absorbing substances. The most important two, maybe three, are water, of course, because percent of us is water. Hemoglobin and oxygenated hemoglobin, and then maybe what I would hope is that you were able to recognize, for example, the absorption spectrum of hemoglobin. I'll show it to you. So also be a little bit familiar with the units. You should be familiar with the units on the axis of such a graph, and things like water absorption is low in the visible, it's high in the near infrared, and blood absorption is high in the visible and low in the near infrared. These kinds of things. Okay, then for scattering, we have the same set of properties. Efficiency, process, and coefficient. Same interpretation. Yeah. For the scattering coefficient, there is one. So the scattering coefficient is formally defined as the density of total scattering cross section, which means that you add all the cross sections of all the particles, all the scatters in the medium, and divide by the volume. If all these particles are identical, then this sum just becomes n times the scattering cross section of one particle, and n over v is again rho, the density. So then but if the particles are different, if you have different particles, you can still calculate the scattering cross section, but then you would add the scattering coefficient, you would add cross sections of the individual particles. One interpretation of the scattering coefficient. So scattering coefficient is as units per meter. Absorption coefficient is units per meter. The coefficient for Raman that you would calculate also as units per meter. And you can think of it as the probability of that process per unit length. So scattering coefficient would be the probability that the photon experiences a scattering event per unit length it travels. So the same thing for absorption. Absorption coefficient is the probability of the photon being absorbed per unit length it travels. And it also means that if you invert scattering coefficient or absorption coefficient, you get something that has units per meter, 1 over mu s as units per meter, and that is then the mean free length that the photon can travel between consecutive events. So if L is 1 over mu s, it means that it is the mean path that the photons, the mean step that the photons take between scattering events on average. The same thing you can do for Raman, for example. Then it will be the mean length that a photon can travel before it is Raman scattered. So it also gives you a measure of the probability of the likelihood of that process. So do you have any feeling for what a typical value for a scattering coefficient is in tissue?
It's millimeters. It's we're not even that. No, it's smaller than that. So it would probably be something like micrometers, like 1 over micrometers.
Yeah, I mean the first answer was not wrong either. So it's usually a little bit in the order of from 1 per millimeter to 1 per centimeter. So that these are typical values. So that means that it would be in the order of let's say the order. So the mean free path could be in the order of millimeters or less. Which means for something that, let's say, it's 1 per millimeter. Again, this means that there's that's a pretty high probability of scattering. Do you have any idea what that so order of magnitude for example for Raman would be if you compare the probability of just normal scattering to Raman scattering? Ballpark feeling for the numbers. Is it in the same order of magnitude? Is it yeah, it's way smaller. So the efficiency of the scattering process can be in the order of let's say 10%, 20%, 50%, whereas the efficiency for Raman is going to be way less than 1%. So that means that through all the calculations, that the coefficient for Raman will be much less, and the length, the inverse of that, would be much higher. So that can be in the order of kilometers. It's a little bit strange, but you can really think of a photo that travels through a very large cuvette of kilometer length, and at the end of it, it will at some point will get around. Okay. We talked a great deal about the size dependence of the scattering focus in terms of range of sizes that you can encounter in biological tissue. And for each of these sizes, there were scattering theories that were appropriate to calculate scattering. So for particles that are really small, the dipole scattering, very small particles, up to particles as large as red blood cells or even larger. These theories were Rayleigh scattering. Rayleigh scattering is for particles that are much smaller than a wavelength. Geometrical scattering is for these really huge particles. And Mie scattering is universally valid as long as the particle is a sphere. So you can calculate it for very small, very large. These are the correct results. But the assumption is that the particle is what I'd like you to know is what I need to put in these theories in order to calculate scattering properties. It's not that much information, you know. What do I need to put in scattering theory to get, for example, the cross section?
Wavelength.
Yeah.
The refractive index of both the medium as well as the particle itself, the diameter of the particle, and I'm visualizing the formula now. I'm missing one thing at the very beginning.
You have them all.
Yeah, okay, that was constant. Yeah.
Yeah. So these four things you need to know. And then that holds for any of these theories. If you know the refractive index, the size, and the wavelength, then you can calculate.
Indices, right?
Yeah. That's both. This is a graphical representation of these theories. So this is the particle radius on the horizontal axis and the scattering cross section on the vertical axis. So Rayleigh theory is valid for the smaller particles here. Geometrical scattering is valid for the larger particles here, and Mie theory that do anything in between. So you can see that it nicely overlaps with Rayleigh low particle in the small particle vision. Okay. Then apart from the coefficient, the cross-section efficiency, to tell you something about the strength of the scattering process. The scattering is the redirection of photons. So we also we need more information if you want to describe the complete process, and that is encapsulated in the phase function. The phase function is the function that describes how light is redistributed over different angles. Obviously, I want you to know what the phase function is. And also because the function is not so convenient to work with, it is usually parameterized in a single number, g, the scattering isotropy. I also want you to know what that is. Anyone know by chance? Yeah, I expected you. What is it?
Now,
Yeah,
it's the fraction. It's the ratio of light that is scattered in the forward direction and backward direction. That ratio.
No, not completely. Yeah, absolutely. It's the average cosine. It's the average cosine of the scattering angle. So not the average scattering angle, but the average cosine of the scattering. And that means that if most of the light is scattered in the forward direction, that means that the angle is close to 0, which means that the cosine is close to 1. And then you will have a g, the average cosine that is much larger. That happens when the particle is large compared to that. So for a large particle, you will see scattering that is light is coming in from this direction. That is predominantly in the forward direction, and you will have a high variation. If the particle is small compared to the wavelength, then light is scattered more or less in all directions, more or less the same, then you will find that anisotropy you get this. All right. Just like as with absorption, for scattering particles as well, it matters how the sample is organized. If you have, I showed you that example of the classroom that was filling with people, and in one hypothetical experiment, everybody could pick a random seat in a random row number, and then if nobody took notice, then at some seats there would be 5 people, at some seats there would be 0 people. Which came with certain statistics. You can calculate the average number of people per row and the standard deviation of number of people per row. But it gets different if you do what we do here. If only 1 person per row is allowed, which means that there are constraints in the placement of the people, then the average number and the standard deviations get different. Now, the same thing happens when you have particles at medium. If, for example, the particles are rigid, so they cannot deform. And obviously they cannot overlap in space. So if they have a certain size, that means that they cannot take any random position that they would like, and that has consequences on the scattering properties. Basically, that goes by this argument. Every particle is scattered electric field, which has a certain amplitude and a certain phase. These phases will interfere at the detector, and if the particles were truly randomly organized, then all of these phase differences would average out. So you would always be able, if you have one particle that gives one phase difference, you would always be able to find another particle that has exactly the opposite phase difference, and that will cancel out. But if there is restrictions because of the size of these particles that can overlap, then that may not always be true. Sometimes they will not cancel. So you have to take it into account, these phase differences, then that is done by a function called the structure factor. And the way that we use it, the way that we incorporate it, so there was a bunch of formulas in the slides which showed the structure factor, but I think this one sums it up perhaps the most easy. If you would have identical particles, which all have an identical scattering cross section, so that's another 10 particles, and you would calculate the scattering coefficient according to the formula. Then at first you would make it with n times the scattering cross section divided by phi, would give you rho over phi times the scattering cross section, would give you the density times the scattering cross section. That would give you this result. Now, when you take into account the fact that particles that are not randomly organized, but there are these phase differences that you need to take into account, this is the modification that you have to do. You need to find the phase function, you need to find the structure factor, both are a function of theta, you multiply them and you integrate them. That gives you a correction factor that is somewhere between 0 and 1. And that tells you that the scattering coefficient is usually a little bit reduced compared to if you would just add all the coefficients together. Yeah, so I want you to know what it is, how you should use it, like this. Incidentally, do you know what would happen if you would? What is the answer you would get if you would integrate the phase function itself over the angular domain? That's a very simple answer. Yeah, 1. Yeah, because it is by definition normalized. So if you would integrate it, is by definition. So that means if the structure factor happens to be 1, then let's say what is here is only integral phase function. So for very dilute samples, so only a few particles, the structure factor is actually 1. So in that case, this whole part simply vanishes. And this is okay. This was the effect of that structure factor. So if you would take a collection of particles and high volume fractions, so high number density particles in the medium. Then the blue curve would be here the scattering coefficient as a function of volume fraction if you would ignore the phase differences. So it simply increase linearly with the number of particles. And if you do include that, then you see that it still increases, but it shallows off pretty fast. So that is the most notable effect. And another effect that is also present is that the phase function of the angular distribution of the light changes because the product of the phase function and the structure factor is shown. Then next topic for Monte Carlo simulations. What I want you to know is the basic recipe for calculating let's say the probability of such a photon path. Meaning that you break it up in sub-events. In this case, that would be the step size, scattering event, redirection into another direction, step size again, scattering event. You break it up in sub-events. You calculate the probabilities for each sub-event. Multiplies these to obtain the total probability of events, for example, this entire photon path. And if there's more than one way from getting here to here, so the field path, you're allowed to have this. So that is the recipe. We also did. I'm not sure if it's assignment, but we did some Monte Carlo sampling, the implementation. So using the probability density function and the cumulative distribution function, that was also a recipe. You take the probability density function, you calculate the cumulative distribution function, you integrate that from zero to from the lower boundary to some value, you equate that to a random number, and then you try to invert that equation so that you get your value as a function of the random number. That is that is all in the document and in the chapter. These are the questions that are associated. Transport and diffusion. We didn't go extremely deep into that, so let's suffice it that these are the main points. You should be aware of what meaning, units, etc. is of the quantities that appear in there. So the intensity again, the fluence rate as well. Fluence rate is the most important one. You want to know what the units of fluence rate is?
Second.
Yeah, it's watt per square meter, so that is joules per second per square meter. So there is a per second in there. It's watt per square meter. So if you would take a small area inside tissue, what the fluence rate would measure is all the optical power that flows through that small area, regardless of direction. So it is basically all the light, all the power, all the optical power that is available at some location. And that is the most important one because you need to know that if you want to do therapy, for example, if you want to destroy something, you need to know how much power you can do. So that was and we talked about transport equations. So I would hope you would recognize it if I show it to you. Identify the terms that are in there. It won't be a big topic on that. For that, the transport equation itself is hard to handle. So therefore, the most popular in our field is the diffusion approximation to the transport equation. That is more important. There was a new coefficient that popped up, the reduced scattering coefficient, US prime. So that's US prime is the product of the scattering coefficient US times 1 minus the isotropy, so 1 minus G, US times 1 minus G. Reduced scattering coefficient. Because it is a diffusion theory, we also get a diffusion coefficient, and that is expressed in terms of the properties as 1 over 3 times this US prime. And very important, this diffusion is an approximation, so it is limited. It has a limited range of things. You cannot use it close to where the light enters the tissue. It is not valid very close to borders between tissue and the surroundings, or etc. So it's important to keep in mind. Okay. Edwin talked about vesicles. I'm just going to focus a little bit on what the possible calculations are that I will ask you to do about this class. But, so you did an in-class assignment where you integrated, or where you estimated how much light the detector picks up if it looks to a particle under certain angles perpendicular to the income light. So that kind of calculation is important. It is of course an application of Rayleigh theory, because these vesicles are very small compared to the wavelength. But you can also use meat theory if you assume that vesicles are spheres, which is not strange to do. Okay, OCT, somewhat bigger topic. I want you to know why you use broadband light sources. It's important that we I want you to know something about the signal formation OCT. That the reference arm in an OCT system essentially acts like a kind of amplifier for a very weak sample signal. If the reference arm would not be there, you would hardly measure anything. But now, having this reference arm power boosts the signal up. How to calculate the actual resolution? That's the resolution in depth. The lateral resolution. That's the other place. The importance of the coherence length for the axial resolution, the importance of the beam width for the lateral resolution. What the difference is between an old-fashioned time domain system and a more modern spectral domain or Fourier domain, SFDI system, OFDI system. I want you to know what shot noise is, where it comes from, what the physical mechanism is, and how it determines the signal-to-noise ratio performance of most of these systems. And then questions like what are common OCT wavelengths? Why would you pick a certain wavelength for a particular tissue type? So with the application. So let's say I would want to do an OCT measurement on the retina. What wavelength range would I choose? Why? So the retina is at the back of the eye, behind 2 centimeters of water. So if I want to image the retina, that means that my light has to penetrate through 2 centimeters of water, then interact and then penetrate 2 centimeters back to get to my detector. So I would want to have a wavelength where the absorption of water is really low. So if I then take my absorption spectrum of water, then I find that it is minimal around 800 nanometers. So that is a good choice. I could go even lower. I could even go to, let's say, 600 nanometers. Can you think of a very practical reason why I wouldn't go to 600 nanometers? It's not a physical reason, it's a practical reason.
Difficult to generate.
No. Yeah, it would be like pointing a laser pointer. Yeah, so 800 is that a sweet mix because it's slightly outside what you can see, and it still has this. For skin, I would pick a different wavelength because I don't have as much water there. So I could go to a longer wavelength. Let's say 1300 nanometers. Why would I do that? Yeah, exactly true. So the longer wavelength is the scattering coefficient for the longer wavelength is lower than for the higher wavelength. So that light penetrates a little bit deeper. So from the image formation, I can just look a little bit deeper. So that point is often. For Raman spectroscopy, Raman's class, what the difference is between Raman active molecules and infrared active molecules. I want you to be able to draw the Jablonski diagrams for these different processes and explain what's going on with these diagrams, of course. The difference between Stokes and anti-Stokes diagram. wanted to be able to do a calculation of the Raman-shift. So if I give you an excitation wavelength and a Raman-shift, can you then calculate the emission wavelength? Or if I give you the emission wavelength and a Raman-shift? And we talked about it just a moment ago, the efficiency of the Raman process, that's really, really low. So you should also do that. So let's know that. This is Sergei's class, so of course you're working on the assignment for him. So the most important points here are the instrumental points. So what is the numerical aperture? That's one term that came back in a couple of times. It's important in OCT. It was important for all the microscopies that we described, and Maruf talked about it as well. So the numerical aperture, what it is, and related to the acceptance angle of microscopes. And that's some basic principles of Dick. Also, Maurice talked about scattering spectroscopy. That again is an application of mainly of diffusion theory. So what's important here? Well, again, when do you use it? What kind of disease can you use it? Is it used for diagnosis or is it used for monitoring or both? So what are typical use cases for that? What's important to interpret these results is that you know the wavelength dependence of absorption and scattering properties. It's again spectral water in blood, but also that the scattering coefficient, like you said, the scattering coefficient decreases with wavelength. Of course, it was also an application of thermal diffusion theory. So there are some pitfalls there, so it's something that can really mess with your data. It's glare, for example. So if you have light that is reflected back from the surface of your tissue right at your camera, then that's light that carries no information. It's just reflected, so that can obscure the image. One of the pitfalls, more pitfalls that we discussed. And I think Maurice also talked about some steps that we take in data processing here, like the standard rule variance, where you subtract the mean and divide by the standard deviation, so you get kind of a normal distribution of or a standardized distribution of values. Process. Okay, then fluorescence. There too, the Blonsky diagrams. What is the physical principle? Why? When do we use fluorescence diagnostics? What kind of diseases? Same thing for fluorescence and for also for Raman and phosphorescence, where we talked about the Blonsky diagrams. So things are important that you can draw the Blonsky diagram, that you can explain it, but also that you know what, for example, the timescales of these processes are. The Raman process is much faster than the fluorescence process, which in turn is much faster than the phosphorescence process. So timescales and efficiencies. So if I ask you to put these three things in order of timescale, then that's the deep. Essentially, that is repeating the same things. Okay, this we have the exam. Not to repeat it. My recommendation is to compile for yourself a list of important stuff, or write down where you can find it in the slides, so that you can quickly find it. So I have a worked out example on Canvas. Here's an example question, just for you to look at here. I think that one is on Canvas as well. So here, for example, I would ask you to draw the Blonsky diagram for fluorescence. There is some efficiency here, so for that efficiency, you can calculate the cross section. For that efficiency, you can calculate with if you know the number density or the volume fraction, you can calculate the coefficient, and if you invert the coefficient, you can calculate the average length between fluorescence events. That would be question. So that would be a question with small calculation. Same thing here. This is about absorption flattening. That would be applying that formula with 3 absorption coefficients in there. And the last one is one example of such a proposition. So I will give you the phase function of two particles, particle A and particle B, and the proposition would be particle A is a smaller particle than particle B. What I would like you to know then, do then is either agree or disagree, and tell me why. Any ideas? So particle A scatters light mostly in the forward direction. Particle B also scatters in forward direction, but it's also more slightly. So what does that tell you about the size of the particle? How do really big particles scatter light? Like red blood cells, for example. Yeah, forward, really high astrometry. So this will probably be a large particle, a very small particle, like a dipole scatters light in all directions. If the particle gets a little bit bigger, it starts to develop for scattering in forward direction, but this particle still scatters sideways. So that means that most likely particle A is bigger than particle B. So in that case, this proposition would be, I guess, close. That's the argument. The argument that I want to make. Okay. So to help you along a little bit, this is again a list of the topics. What I have crossed out are the things that I will not ask about at the exam, so that helps you a little bit. And also the ones that are great are the ones that you have had a lot of work done in the assignments already. So if anything, it will be a very small part, so that also you can focus on these other things that help you. Okay, that's it, guys.
Yeah.
Yeah, go ahead. Oh, that's no, I guess not. I think I thought. Yeah.
Heb je wel eens de B en dit in dan? Kijk, dit is die B en dit. Zo. Kijk, maar dit is ook gewoon een hier, kijk, ik kan hem helemaal zo.